And the main difference between the Jacobi method and the Gauss-Seidel method is that in Gauss-Seidel method, we will be using the most current updated values of the variables, whereas in Jacobi method, at every step, we will use the of the previous values of the variables of the previous step. So we'll see how what I am telling you, it will be clear to you once I describe the algorithm to you. So as you can see here, this Jacobi method, this A matrix, that is the coefficient matrix, is given to us, and the source matrix or the RHS matrix is B, which is 1, 2, 4 here. And in this method, since it is an iterative technique, we need an initial guess of the solution. Whatever iterative methods we will be discussing after this also will have a initial solution. That is, an initial guess to the solution will be given to you, and based on that initial guess, you have to approach towards the actual solution. So, so we'll also see how the initial guess is determining the convergence of a solution, whether any initial guess can work for converging towards the solution. We'll see that in the later classes. So as you can see here, from A and B, we can form the equations, right? That is AX plus B equals to C. AX equals to B. That kind of equation we can form from the matrices. So first equation here is 2x1 plus x2 equals to 1, and x1 plus 2x2 plus x3 equals to 2, and x2 plus x3 is equal to 4. These are the three equations that we have with us, which we need to solve using the Jacobi method. So the first step in the Jacobi method is, from each of these equations, we will find an expression for each of these variables. That is, here there are three unknowns, right? x1, x2 and x3. So from the first equation, which is 2x1 plus x2 equals to 1, we will try to find out x1 in terms of the other variables x2 and x3. So here you can see x1 will be equals to 1 minus x2 by 2, right? So I'll write this here. So from this equation, we can get x1 equals to 1 minus x2 upon 2. Similarly, from the second equation, we'll try to find out x2 in terms of x1 and x3. So it is 2 minus x1 minus x3 upon 2. Similarly, for the third equation, we'll try to find out x3, which is 4 minus x2. So these are the three equations which we have formed. So what we'll do is we'll iterate using these equations. So in the first step, that is the first value of x1, that is we are writing x1 of 1 equals to, from the first equation we can write 1 minus x2 of 0 by 2. And x2 of 0 is x of 0 matrix is given to you, that is the initial solution, which is 1, 2 and 1. Right. So x2 of 0 is 2. So we'll get minus 0.5 as x1 of 1. Similarly, we'll try to find out x2 of 1, which is 2 minus x1 of 0 minus x3 of 0 upon 2, which is 2 minus 1 upon 2, which is 0. Similarly, we find out x3 of 1. So finding one set of values of x1, x2 and x3 completes the first iteration, or the first step towards solving the equation. So once the first step is completed, we move to the second step. What is x1 of 2? It is, the equation is same, 1 minus x2 of 1, that is the value of x2 obtained in the previous iteration, by 2. Again we'll get some value. Similarly, we can find out x2 of 2, x3 of 2. Then again we can do third step, fourth step, like that we can continue. So now the question arises, what is the stopping criteria, right? Means up to how many steps we will do, how do we know what is the exact solution? So what we do is, basically after every step, say after step 1, we have got x matrix as x of 1 minus 0.5, 0 and 2, right? So once we have got that, and the value of x matrix at the previous step was 1, 2 and 1. So now we can see here that the difference between these x values at the two instants, that is x of 0 and x of 1, we can find out. So what will be the error or the difference between x of 0 and x of 1? We can directly subtract each of these values and we can see the percentage difference. So if the percentage difference between x of 0 and x of 1 is below a particular tolerance limit, then we can stop our iterations. So we'll see that in the MATLAB code. Similarly, after step 2, we obtain x of 2 as 0.5, 0.25 and 4. So once we are done with this, again we have to check what is mod of x of 2 minus x of 1 by x of 1. So this will give you the error at every step. So if it is below the tolerance limit, then we'll continue. Otherwise, we'll stop our iteration here. So is this method, is the logic clear, the Jacobi method, or any clarifications are needed? Anyone? Is it clear?
Yes, sir, clear.
Okay. Anyone, any confusions? Okay. Okay, fine. Then we can move forward. So now, similar to the Jacobi method, we have another iterative technique to solve the equations, which is the Gauss-Seidel method. So what is the basic difference between the, we'll try to see what is the basic difference between our Jacobi method and our Gauss-Seidel method. So in Gauss-Seidel method, we can see here, uh, it is a similar kind of process we will follow, but what is the difference here? Just see here, in the first step, we are doing x1 of 1 equals to 1 minus x2 of 0 by 2. So it gives me 0.5. However, in the second step, you just carefully note here, x2 of 1, previously we were using 2 minus x1 of 0. That is, first step, we were in the first step and we were using the values of x of the previous step. But here what we are doing in the first step itself, since we have already found out x1 of 1 just in the previous step, we will be using here x1 of 1, not x1 of 0. That is the most updated value of the variable we will be using. So it is 2 minus x1 of 1 minus x3 of 0. x3 we will be using 0th value only because we have not yet obtained x3 of 1, right? Divided by 2. So that gives me 0.75. Now we move on to x3 of 1. What is x3 of 1? x3 of 1 is 4 minus x2 of 1, which is equal to 4 minus 0.75, which is 3.25. Again, we will calculate the error after the first step like the previous one only. We will take the x matrix in the first step and the previous step. We'll subtract that. We'll see the percentage difference. And if it is below the tolerance limit, we'll stop. Otherwise, we will continue. So in the second step, again, x1 of 2 is 1 minus x2 of 1 by 2. Similarly, x2 of 2 will be, here again the change will come, that is x1 of 2 will be using, not x1 of 1. In this way, we can do our solution and so in MATLAB we will be seeing how many iterations is it taking for me to complete the solution. So basically we will see there that Gauss-Seidel method, since we are using the most currently updated value of x at every step, it will take less number of iterations to complete rather than the Jacobi method. The Jacobi method will be taking more number of steps or more iterations to complete our to approach to the exact solution. So we'll see that. So this was the this last class there was some network issue, so I could not complete the this discussion. So today I will show you the MATLAB code for the Jacobi method, and then will discuss. We'll try to understand the Jacobi method MATLAB code. I'll show you the output, everything, the plot for the solution. Then for next class you have to submit the MATLAB code, or the homework will be to submit a MATLAB code for the Gauss-Seidel method. So once you do Gauss-Seidel method, then we can compare the Jacobi method and the Gauss-Seidel method, and you have to report the number of iterations, the value of x at each iteration, and the final value of x. So, okay. So before going to the MATLAB code for Jacobi method, we need to understand one more important thing. Is this concept clear? Any doubts?
Yes, sir, clear.
Clear, right? Okay. Okay, so for the MATLAB code, actually, we have to develop a generalized code, right? So we cannot do it for a particular form of equation. So we need to have a generalized expression for x1, x2, x3, and then we can move forward using that. So one second. See, so this is my general equation for a 3 variable equation I am doing, then I can also extend it to an n variable system, n cross n system. So see here, the first equation is a11x1 plus a12x2 plus a13x3 is b1. Similarly, we have the two other equations. So what was our target? So from the first equation, we wanted to find out x1 in terms of x2 and x3. So it is basically b1, that is the term on the right hand side, minus a12x2 plus a13x3 upon a11. Similarly, x2 was b2 minus a21x1 plus a23x3 by a22. And x3 was b3 minus a31x1 plus a32x2 plus a33 divided by a33. So if you see these three equations, you have to find a generalized expression for x of n. So is it possible? We'll see here. See, if we write x of xk, okay, fine. So xk is, we can write bk minus sum of k, one second. So we can write bk minus summation of k equal to, not k, we'll write here I equals to 1 to n, I not equals to k, a ai xi divided by a kk. See, if you can understand this one, then your problem will be solved to write the MATLAB code. See, xk, that is when we are concentrating on x1 here, x1, right? So you can see here in this bracket term, there is no x1 here. So first of all, that is clear, right? And when it is x1, it is b1. When it is x2, it is b2. And when it is x3, it is b3. So basically, xk can be written as bk minus a sum of these terms when I equals to 1 to n and I is not equal to k. That is for x1. This x1, for finding out x1 in this sum, this x1 term will not be there. So if you expand this one, it will be basically a1 and I will be not equal to 1, right, for the first x of 1. So a12 x2 plus a13 x3 divided by a of 1 comma 1. Similarly, we can also find out for x2 and x3. So this is my generalized expression for writing the MATLAB code. Just we have to remember this one. We'll see in the MATLAB code whether we have implemented the same expression. Okay, now we'll see the MATLAB code. Is this clear, this generalized expression for the Jacobi method?
Yes, sir. It's clear.
Okay, just a second. I'll share the screen. Just let me know if you are able to see. Second. Are you able to see the screen? Are you able to see the screen, anyone?
Yes, sir.
Okay, the MATLAB screen you can see, right?
Yes, sir.
Okay. So here we'll see the MATLAB code first. So you can see here for the Jacobi method, in the 6th line, I have taken the input for the coefficient matrix. 8th line is the input for the RHS matrix. Then we are trying to see how many unknowns are there. That is n equals to length of B. And this is the x value at the 0th solution, the 0th iteration level. That is in the 12th line, we have proposed our initial solution. We have given the initial solution. Then for the error value, some initial value you can take anything larger than the tolerance value. So that the initial value is for, so that the control goes inside the loop for the first time at least. And k is 2 here we have taken to track the number of iterations. Similarly, for sum is to find that sum I equals to 1 to n, I not equals to k. That term, in order to find that, we have taken that sum one variable. So now we are giving a while loop. We are using a while loop till the error is greater than equal to 10 to the power minus 4 we have used here. This is the stopping condition. And then we are using a loop from nested for loop for 1 to n ii, and for jj also 1 to n. And this condition we are checking if ii is not equal to jj, then we are summing, that is sum 1 equals to sum 1 plus a into x. And be careful here, since it is the Jacobi method, we are using x of jj comma k minus 1. That is the value of x at the previous iteration, not the current iteration. So this gives me this for loop actually gives me this sum, and ii not equals to jj is because in the sum we had a condition I equals to 1 to n, I not equals to k, right? We want to omit that one term. That's why we are using that condition. Then once we get sum in the 31, line number 31, we are using x of ii comma k, that is the value of x. K is the number of iteration and ii is the index of the variable, that is x1, x2, x3, like that. So it is basically b of ii minus this summation divided by a of ii comma ii. And then after we get x, we have to reinitialize sum equals to 0, because for the next variable, that is x2, again the sum has to be calculated from the beginning. That is, there is no relation between sum of x1 and sum of x2. That's why we are reinitializing sum 1 equal to 0. And in line number 37, 39, we have basically calculated the error. So as I was telling you, this error is actually a matrix, right? Because we have say for the case, that is for, say we are finding the error at the end of fourth step. So we have an x matrix, that is x1, x2 and x3, three values of x at the third iteration. We have a value of x, that is the x matrix, x1, x2, x3 at the fourth iteration. Now how do we find the error? Error has to be a single value, it cannot be a matrix. So if we subtract x3 and x4 and divide it by x3, we'll get a matrix. So basically we have to take uh, the average of that matrix, that is sum of the elements of that x1, error 1, error 2 and error 3. Then we have to average that. So that is what we are basically doing here at error 1. So in line number 39, we are basically using we are trying to find out the error matrix, and then in line number 43 we are trying to find the average of the error here. Then we are in line 45, we are incrementing the iteration by 1, and then again we are reiterating the same thing. Any confusions or any doubts in the MATLAB code? Anyone? I'll run the code and show you, but before that, any doubts, anyone? Is it clear? Any doubts? Srinjoy, is it clear?
Yeah, yeah, yeah. It's okay.
Okay. Okay, fine. Okay, so I'll run the code and show you. Just run the code. We'll go to the, so it is asking me to enter the coefficient matrix, right? So I'll enter the coefficient matrix, which is 2, 1, 0. So remember, when we enter a matrix in MATLAB, so it will be basically the row, single row we have to enter first, then we have to place a semicolon, then enter the second row. It is 2, 1, 0, 1, 2, 1, 0, 1, 1. This is the coefficient matrix, and source matrix is, so the source matrix is a column matrix. You have to enter in that format only. So basically, you have to give semicolon after each element. 1, 2, 4. Right? It is done. So I'll just use a print statement here. Second. So this is the coefficient matrix, this is the source matrix. We'll see the values here. So this is the value of x, and we will be seeing how many iterations we'll see. So see you can see the value of k as 53, which shows the number of iterations. So we have in X matrix, it is basically 3 cross 53. That is 3 rows are there, x1, x2, x3. For every iteration, we have the values. So the final value is at the 53rd column. That is x of k we need to find out. Second, x of colon comma k. That will give me k. So you can see here this x of colon comma k minus 1, it gives me 2.99 minus 4.99 and 8.99. So basically the solutions are 3 minus 5 and 9. So it took me 53 iterations to reach to the exact value. So now if I plot this one, so it is basically x of 1 comma colon. So x of 1 comma colon means along the row, the first row I am plotting, that is the value of x1 from first to the last iteration. So you can see in this plot, initial value was 1, then it dropped to minus 0.5, then it gradually increased, and you can see after some iterations, it gradually converged to 3. Are you able to see the plot in the MATLAB screen? Are you able to see the plot on the MATLAB screen?
Yes, sir.
Okay. So this is x1. Now I will plot x2 also. So if you give hold on command, basically in the same plot, you can plot another figure. Plot x of 2 comma colon. Then we'll plot the third value also. So you can see here, I'll just magnify them. So these are the x1, x2 and x3. The blue line represents the value of x1 at different iterations. The red one represents your x2, and the yellow line represents your x3. So you can see here that initially there are some oscillations in the values of x1, x2 and x3, and as the iteration progresses, the x-axis is the number of iterations, right? And we can see here it smoothly converges to a particular value. Is the MATLAB code clear? Any confusions? Anyone? Any doubts or any confusions? Anyone?
I have a doubt, that is the plot of x in bracket x under bracket 1 comma colon. What does it means? Can you again tell that?
I'll tell that. So basically, if you have a matrix like this, suppose x is equal to 1, 1, 2, 3 in the first row. Second row, I'm giving a general example. Suppose you have 1, 2, 3 in the first row. In the second row, you have 4, 5, 6. And in the third row, you have 7, 8, 9. So this is my matrix, right? So if I write x of 1 comma colon, that is basically the first row of that matrix. And if I write x of 2 comma colon, that is basically the second row. Now if you want the first column of the matrix, we have to write x of colon comma 1. So if it is x of colon comma 1, if you write, that will give you the first column of that matrix. So 1 comma colon is the first row of the matrix.
Yeah, understood. Thank you.
Okay. Anyone else? Any other doubts? Any confusions? Javed, any doubts? Any confusions? No confusions, anyone? So can I progress? Okay. Any doubts, any confusions, anyone? Just last time I'm asking once more before I start the new module. So your homework will be here to implement for the this Gauss-Seidel method, and I'll send you the code for the this Jacobi method, and you have to compare the solutions of x1 using Jacobi method and the Gauss-Seidel method. Value of x2 for Gauss-Seidel and Jacobi, and x3 for Gauss-Seidel and uh, Jacobi method, and you have to report the number of, as I have written in the question, the number of iterations, the values of x along all the iterations, and the plot of x1, x2, and x3. Just I'll wait for 2 more minutes, then I'll move to the next session, next module we'll see. Okay, so I'll move to the next topic or the next module. So till now we were seeing the different iterative techniques and different techniques to solve linear equations, right? So now we will be seeing how to solve non-linear equations using different numerical approaches. Non-linear equations and numerical techniques to solve them, right? So here we will see. So till now we were seeing different linear equations, right? Like of the form of ax equals to b. So if the equations are of the form ax equals to b, we generally call them linear equations. So now what is a non-linear equation? So any equations which involves different algebraic terms, different mathematical transcendental operators like the logarithmic term or the trigonometric term or the exponential term, those type of equations we call as non-linear equations. So before we go to nonlinear equations, I'll just quickly brush up some basics about the nonlinear equations. So before we go, we have different in an equation, we have different variables, right? Then we have, using those variables, we form different mathematical expressions. These expressions, when equated to a particular type of value on the right hand side, we call them as functions. Then we have different type of functions. Then we have, when we equate these equations, these functions or expressions to different values, then we form what is called an equation. So in that equation, we have linear and non-linear equations, right? So I'm giving you an example for non-linear equations. Suppose we have an equation x cos x plus 1 equals to 0. So this type of equations is not possible to be solved by any analytical technique. Either you have to use a graphical approach or you have to use any numerical technique. So we'll discuss that. So any numerical technique is basically of two types. The first type is the bracketing method, and the second type is the open methods. So in bracketing method, we have two types of methods. One is called the bisection method, and the second is the regula falsi method, or it is also known as method of false position. We'll see each of these methods in details. In the open methods, we have the fixed point methods, then we have Newton-Raphson method, and we have the secant method. So basically, what is the difference between this bracketing method and the open method? So in bracketing method, the root, that is the solution to the equation. So in all these types of methods, we will be given with either one or two initial solutions. Based on those initial guess of the solution, we have to will be approaching towards the actual solution. Okay, so now in bracketing methods, your root will always bracket, that is, it will be always within the limits which is given by the initial root. That is, we'll see how it is bracketing. In bisection method, suppose we will be given that your root lies between a particular limit. That is, it will be an equation will be given to you, and then it will be told that the initial interval for the root is 1 comma 2. Suppose it is told 1 comma 2. So that means your root lies between 1 and 2. So that is called bracketing the root. That is, your limit is enclosing or bracketing the root. Whereas in open methods, we don't have such kind of bracketing. Bracketing thing is not there. That is, your initial guess will be given to you, not an interval, and your root will not be bracketed. That is, your root will not be enclosed by the limits of the initial solution. So this is the difference between the bracketing method and the open method. Okay. So now we'll see that just a basic some in equations, as we discussed about variables. So the building block of any equation or an expression is a variable, right? So what are these variables? We have different variables x, y, z, a, b. These are the different variables which can take any value according to the equation, right? They don't have a constant value. Now using these variables, we will have different expressions or functions. So the expressions are, suppose using x and y, we form an expression which is 4x plus 5y, or we have 3x plus 2y plus z. Like this we can form different kinds of expressions. Then we have equations. What are equations? So when some conditions are applied on these expressions, some mathematical conditions are applied on these equations, then it forms an on these expressions, sorry. When some mathematical conditions are applied on these expressions, then it is called an equation. Like we have the expression, right? 4x plus 5y. When I tell 4x plus 5y equals to 3, so I'm putting a mathematical condition on the expression that 4x plus 5y is an expression or a function which is equals to 3. So that is an equation. Or if we put 3x plus 2y plus z equals to 65. Again, we are putting a condition. So that gives me an equation. Now, this expressions or functions, right? So there can be different kinds of functions. Like in functions, what are the different kinds of functions you can think of? One is the polynomial or the algebraic functions, right? The algebraic or polynomials, polynomial functions. Or we can have non-algebraic, or which are called as transcendental functions. Like algebraic functions will be of the form a naught of, say, x naught, a1 x1, like this, an x to the power n equals to some bn. So this is the general form of any algebraic or polynomial function. This non-algebraic or transcendental functions, they don't have a general form, right? So it can be exponential equation, that is terms consisting of exponential terms. Then we can have trigonometric terms. Then we might have your logarithmic terms, or we can have, these are the different transcendental equations or combination of all these exponential, trigonometric, logarithmic, any combination of all these equations. So like examples can be given. If you have log x plus e to the power x plus cos x equals to 0. These are transcendental equation. So these algebraic equations we can solve either by some small, if the polynomial or the, if the polynomial function is of a lower order, that is a second up to second order or first order, then we can solve it using analytical techniques. But if it is a higher order polynomial, then there are only two options to solve the equation. Either you have to use the graphical method, that is you have to plot the equation and then find out the solution, or you have to use a numerical technique. Whereas in transcendental equations or functions, like the non-algebraic functions, which consists of the combination of different types of expression like exponential, trigonometric, logarithmic, we don't have any analytical solution. We don't have any analytical technique to solve those equations. We have to solve them by any numerical technique or by any graphical approach. Graphical approach can also be difficult in these equations because it is not always easy to plot a graph for a random function. So this is the basic. Before we move into the details of these methods, so n here, that is it is known as the degree of the polynomial, right? So if it is n equals to 1 means it is a linear polynomial, and n, if the order of degree of the polynomial is greater than 1, it is called a non-linear polynomial. Okay. So I'll just first I'll give a basic introduction about the graphical approach, a generalized graphical approach. Then we will. So what is told in the graphical approach? So I'll take a random function and I'll plot it. I don't know what is the equation. I'll just use a random plot. Second. So if this is the axis, suppose we have a plot like this. Second, you have a plot like this. So can you tell me how to find out using this graphical approach? From this graph, at least, can you tell me what are the how many solutions are there for this equation? Okay, so before that, I need to tell you something. Suppose you have the equation is fx equals to 0, right? So what does this mean actually? So fx equals to 0. So that means you need the values of x for which the function is 0. So now in our axis, in our normal xy axis, if we just plot it here, what is the which is the x equals to 0 line? Can you show me here or plot it? What is the x equals to 0 line? Anyone?
The line will be parallel to the y-axis.
Yes, can you repeat once again?
The line will be parallel to the y-axis.
X equals to 0 is a line parallel to the y axis.
Yes.
Anyone else?
It will be line parallel to the x-axis.
X equals to 0, I am telling, right? So
Hmm.
it is neither the line parallel to x axis nor a line parallel to y axis. It is the x axis itself. It is the x axis itself, because along the x axis we have x equals to 0, right? Sorry, I told the question in a wrong way. So basically we have to plot y equals to 0 line, not x equals to 0, because see here the equation is f of x equals to 0. So why we are when we solve this, we can write it like this: f of x equal to y and y equals to 0. These are two equations. When we combine these two equations, we will get our, if we combine these two equations basically, then we will get fx equals to 0. So if we plot this type of equation, fx equals to y, that is y equals to the function, and y equals to 0 separately, then if we find the intersection point of these two functions, these two plots rather, we can get to the actual solution. So y equals to 0 here, it is the x-axis, right? Y equals to 0 is the x-axis, and say we have a plot for y equals to f of x. So then suppose we have some plot here, some plot you have. So then these are the points which are the intersection points of this graph with the x-axis, right? So now if we come back to this figure here, this black line is the y equals to f of x line, and this x-axis you can see here, this is the red line, right? This is the y equals to 0 line. So we can find the intersection points of this curve with the x-axis. This is the first one, this is the second, third, fourth, fifth, sixth, seventh, eighth, ninth. Is it clear? Why we always, when we find the root of any equation, we find the intersection of that plot of that function with x-axis. Why we do that? I explained that to you. Is it clear to you, or should I explain it once again? Any confusion, any doubts, anyone?
No, sir.
Clear, right?
Yes, sir.
Okay, fine. So this is the basically the idea behind the graphical approach. And what we do in graphical approach is we have to plot that equation, and then you have to manually find out what are the intersection points of that plot with the x-axis. Then we will approach to the solutions. So again, there's a disadvantage with this graphical approach. Every time it is not possible to plot the graph of any random equation. It is obviously possible, but it will be a cumbersome process. So instead of that, if we have a more intuitive and more mathematical technique, so that will be better to you, right? Okay. So one more thing I want to show here, that is, so suppose if it happens that you have a graph. So this is x, this is y. Suppose you have a plot of some y of x which is like this, right? So this graph never intersects with the x-axis. So how to find the solution of this equation? Suppose this is f of x and it is asked f of x equals to 0, you have to find out. So if it doesn't intersect with the x-axis at all, so in such a case, we will say that this equation has no solution. So this equation has no solution. And the case which I described previously, it had multiple intersection points, right? So we will tell it as multiple solutions. There are multiple solutions to this equation, equation. If it intersects at one particular point, we will say it has a unique solution, right? Suppose you have another graph. I'm plotting it in the same curve, same axis. Suppose you have an equation like this. So it is intersecting at only one point. So this will be known as an unique solution. So what we can conclude from this is, based on the nature of the graph, we can categorize the solutions of fx equals to 0 as, there are three kinds of solutions, right? One is an unique solution. Second is your multiple solution. And third is your no solution. These are the three kinds of solution which can exist, right? So now we will see the first method, which is your bisection method. So first we will look into, so here again, there are three methods here: bisection method, then you have the secant method, then you have the regular falsi method. So here I will be discussing the MATLAB. First I'll discuss the mathematical technique to solve the equations. Then we'll move to the MATLAB coding for that. So in the bisection method, what we do is we'll take a function, and then first we'll see the mathematical approach, then we'll see the graphical approach, right? Just a second. Just give me 1 second. Just give me 1 second. Some network issue is coming. I'll just resolve it. Okay. So in bisection method, first we'll look into the mathematical approach, then we'll see the geometrical thing. Okay. So here, suppose you have a function which is given f of x equals to x cos x plus 1 equals to 0. Okay. So now it is given the initial bracket is, that is the initial, your solution lies between -2 and 4. So this is given to you. So now what is the algorithm? So first we have to prepare a table. So what is that? Okay, first let me discuss the geometrical approach. It might be more appealing to you. So suppose this is my x. So this I'm doing for a random function, right? So you can see here, your root is here, right? So this is your root. So suppose our initial bracket is given as -2 and 4. This is -2 and say this is 4. Okay. So you can see here our root, which is where the function intersects the x-axis, that lies between -2 and 4. So our initial bracket is okay. So now we need to find out an intermediate point, that is the midpoint of these two values. So this I am taking as a, that is the lower limit, and the upper limit is b. So if we take an average of this upper limit and the lower limit, what we will get, that is, if we find out c is a plus b by 2, so that is basically 1, right? 4 minus 2 is 2, 2 by 2 is 1. So here somewhere we will get c. This is a, this is c at the first iteration. It is basically 1. So what we'll do is, once we get c here, we will draw a line vertical to the y-axis till it intersects the graph. Okay. So now it intersects the graph at say some value, and we'll find what is that value. So this is basically f of c, right? So now your f of c here is greater than 0, right? So what we will do is, we'll shrink our limit. That is, we will move our a, since f of c is greater than 0, this will be your new a. This c will be your new a. This will be, this was a of say 1, this was b of 1. So for the second step, this is your A, that is A at second step, and your B will remain as same. So now our initial root limit was between -2 and 4. In the second step, what we did is we shrinked our root limit between 2 and 1 and 4. So it is shrinking. Again, in the next step, what we will do is this is A, this is B. So A is 1 now, B is 4. So 1 plus 4 is 5. 5 by 2 is 2.5. Suppose somewhere here. One second. Okay. So if we find out 2.5, it is somewhere here. See, this is C of 2, which is 2.5. Now again for for this C, we need to find out what is the functional value at this point. So this functional value here is negative for this C. So this is my f of C2. Since it is negative, now what we will do is we'll shrink our limit again, but this time we'll shrink the upper limit. That is B will change. Now your limit is A will be same here 1. However, your B at the third limit will be this C of 2, that is 2.5. So in the first step, our root was between -2 and 4. In the second step, it changed to 1 and 4. In the third step, it changed to 1 and 2.5. So you can see as we move through these steps, our limit of the root is shrinking. That is slowly what will happen is this upper, as the root converges, so our upper and lower limit will be almost equal and will your root will converge into one value. Is this concept clear? Any doubts? Any doubts, anyone? Javed?
No, sir.
Javed, any doubts? You're not talking today? Okay. Okay, so this is the concept that with every step, what we are doing is we are shrinking the limit of the root. That is, first it was told, again I'm repeating this, your root was between -2 and 4. Then it shrink to 1 and 4. In the third step, it shrink to 1 and 2.5. Then gradually it will shrink even closer and then will converge to one root. And for this, you must remember one thing, that is f of c. If it is greater than 0, then you have to change the lower limit to c, and if it is in the upper limit, if the f of c is less than 0, then you have to change the upper limit. So this is the concept behind the geometrical approach behind your bisection method. So now we'll try to solve one problem by hand first, by mathematical operations. Then we'll see the MATLAB code for that. So first what we have to do is we have to prepare a table for this. Your A, B, you have your C equals to, okay, first we'll write the f of A. Then you have f of B. Then you have C, which is, then you have your f of C. Here is the k, or the number of iterations. So in the first iteration, your A is -2, B is 4. So f of -2, I've just calculated this. If you have to your function is x cos x plus 1 equals to 0, right? So basically you have to, in this, you have to substitute for x as -1, -2 and 4. Then you have to find out f of A and f of B. So f of A is 1.83 and f of B, that is f of 4, is -1.61. C is half of A plus B. That is the midpoint of A plus B. A and B, that is 1. So then we have to find out f of C, which is f of 1. Again, it is 1.54. So in the second step, since f of C is greater than 0 here, we'll change the lower limit. So it is between 1.54 and 4. Then f of a is f of 1.54. Sorry, it is not correct. So a will be equals to c, right? So it is 1 and 4. F of 1 is 1.54 and f of 4 is minus 1. B is same, right? So f of 4 remains same. Again, we have to bisect between 1 and 4. So it is 2.5. F of 2.5 is around minus 1.01. So in the third step, A is now, since this f of c is less than 0, your A will remain same and B will change to 2.5. And f of a will again remain same 1.54 and f of 2.5 is minus 1.01. So c is the midpoint of 1 and 2.5, so it is basically 1.75 and f of c is 0.68, rather 0.69. Will round off to two places. Again in the fourth step, your f of c is again greater than 0, so your lower limit will change to c. So now it is 1.75 to 2.5. F of 1.75 is 0.69 and f of 2.5 is minus 1.01. C is again the midpoint between 1.75 and 2.5. It is 2.125. F of 2.125 is minus 0.118. Like this, we have to continue until this f of c approaches almost to 0. Because if f of, so what is the solution actually? If C will be the final solution. The value of C when f of C is almost 0, that is it crosses the tolerance limit, then we can say that our solution we have approached to the actual solution. Okay, so now we will see the MATLAB code for this. Just a second. Sorry, I'll share my screen first for the. Okay, so what we'll do is we'll first cover all the methods, then at last we'll see the MATLAB codes. Okay, that will be better, I think. So, so in this way, we have to continue till this f of c approaches to 0. That is, it crosses the tolerance limit. Okay, so this is about the bisection method. And so why is it called bisection method? Is it clear? So it is called bisection method because at every step we are bisecting the interval. So initially it was between minus 2 and 4. We bisected and we found the midpoint as C, which is 1. Then again we bisected 1 and 4. Again we are we are finding the midpoint and making it as a new limit. So because we are using that midpoint approach here, it is known as it is also called as a bisection method. So now we'll move to the second method, which is your. Okay, just take a 5 minutes break and I'll come back. Okay, so I'll start with the second method. Just like the bisection method here, there is one more method. So, so in second method, first I'll explain the algorithm, then I'll go to the geometrical approach. So what we do here is the first step here. So you need to understand what is the difference between the bisection method and the secant method. So in secant method, basically we have unlike the bisection method, which was a bracketing method, that a limit of roots was given to you, right? So here you will be given the directly the initial guess of the root. So there will be, we'll start with, so we'll be starting with two initial guesses. So then we have to, in the graph, we have to locate, suppose the two initial guesses are say x1 and x2. We have to locate x1, f of x1, x2, and f of x2 in the graph. Then we will be between f of x, we have to draw a secant connecting f of x1 and f of x2. Then we have to find the x-intercept of this secant. That is the point at which this secant intersects the x-axis is x3. Now our limit will change. Now we have to locate x2, f of x2, and x3 comma f of x3. This we have to repeat until you converge. So I'll show you in the graph how to do that. So 1 second. Suppose you have the axis like this and you have your plot somewhat like this, and your initial guess is given to you. Say this is the value of x1, and this is this is the value of x2. So what is your solution here? This is my solution. So x1 and x2 are given to me. Now I'll try to approach towards the exact solution. So what was told, first we have to locate x1, x2 we have located. Now we have to locate f of x1 and f of x2. That is, we have to draw a vertical line from x1, and we have to identify the point at which it intersects the graph. So this is basically f of x1 and this is f of x2. Then we have to draw a secant joining these two lines, right? So this is my point here where it intersects. Joining these 2 points, we have to draw a secant like this. Secant means a straight line joining these 2 points. Since the graph is a curve, so we are calling it as a secant. Now we have to find the x-intercept of this particular line. So what we have to do, we have to extend this line till it intersects the x-axis. So this is my x3. Then we have to repeat this same thing using x2 and x3, right? So again from x3 we have to draw, if I just zoom in here, so this is my x3. I draw another line vertically. This is my this point, and this is my another point. So if I draw another secant here, it is almost like this. Again, if I suppose it intersects here, so this will be my x4. Again, I have to repeat with x3 and x4, and we'll see that slowly the secant, the x-intercept of the secant will converge towards the actual root. Is the geometrical approach clear or should I explain it again?
Sir, can you please explain again?
Yes. So where is your confusion? Can you tell me? Then I'll explain it better.
Sir, last portion.
Okay. So this x1 and x2 are the initial guesses which are given. Based on x1 and x2, we have to find the actual root, right? So what we will do is at x first we have to locate x1 and x2 and the corresponding functional values. That is f of x1, f of x2, and then we will draw a secant. There is a black line here joining these 2 points, and then we have to extend this line till it intersects the x-axis. It intersects the x-axis at a point, say x3. So if I zoom it here, you can see. So x3. Now we have to repeat the same thing with x2 and x3, right? So x2 is here. This is x2, right? And this is the point, and this is another point. Again, we are drawing a straight line joining these 2 points, and then we are extending it so that it intersects the x-axis. So it intersects the x-axis at say x4. Again, we will do the same thing with x3 and x4, and then we will see that this secant, it will intersect the x-axis at exactly the root point. Then we will converge to the solution. Is it clear?
Yes, sir, clear.
Okay. So now this is the geometrical approach, right? So we need to find a mathematical expression in order to solve it. So we'll try to find a mathematical expression. So if you see here, this one, this black line, what is the slope of this black line? If we try to find out the slope of the secant, it is basically y2 minus y1 by x2 minus x1, right? So it is between x2 and x1. So it is f of x2 minus f of x1 upon x2 minus x1. This is given by the slope, that is m. So if we want to find out the equation of the secant, so it is basically y minus y1 equal to m into x minus x1, right? So it is y minus y1 is f of x2. Slope is this one, f of x2 minus f of x1 upon, this is m. Then you have x minus x1, right? So x here you have to carefully note this. So here we are trying to find the equation in terms of x3 because this x3 is changing every time. Now we have x3, then next iteration it changes to x4. So this x3, if we make it as a subject and if we find the equation of the secant in terms of x3, then we can directly equate, we can find the value of x3. So instead of x here, we will be using x3, that is x3 minus x1. Now, if we want to find the value of x3 in this equation, what is the value of x3 here? Rather, I'll not write x3 here. I'll write it as x only, generalized x. Okay. So this is the root we are trying to find out. We'll write as x only. So now if we want, what is x3 here? It is the point where this secant is intersecting the x-axis, right? So if in this equation, if we substitute y equals to 0, so that will basically give me the x-intercept, or that will give me the exact solution, right? So in this equation, if we substitute y equals to 0, in this equation, what we will get? It is minus f of x2 equals to, sorry, this is x2, x minus x2, f of x2 minus f of x1 by x2 minus x1. From this, if I try to find out x, what is x? It is x2 minus f of x2 into x2 minus x1 by f of x2 minus f of x. So this is the generalized expression. This is the generalized expression for finding out the root using the second method. Or if we generalize it further, so it is, this is x3, right? So it is x of k plus 2 equals to x of k plus 1 minus f of xk plus 1 into xk plus 1 minus xk by f of xk plus 1 minus f of xk. So this is the generalized expression. So here you can see, first we will be finding out xk plus 2. So before that, since in second method I told there will be two initial guesses will be given to you. Xk and xk plus 1 both will be given to you, right? So you can see here xk must be known as well as xk plus 1 must be known. Both must be known, then only you can solve this equation. So now we will see the MATLAB code for this. Is this clear? Any doubts, anyone? Any confusion? Srinjoy, any confusion?
No, no, it's okay.
Okay, so I'll show the MATLAB code for this. Is the screen visible?
Yes, sir.
Okay, so here in bisection method, first I'll show for bisection method, and the second method, it will be a homework for you. So you have to, last week there was no homework. So this week there will be two homeworks. So in bisection method, what we are doing is, first we are declaring the second line, we are declaring the x variable, that is sims of x. Sims basically means it is a symbolic variable. In MATLAB, if you want to declare any variable, you have to use the sims command. Then we are using the function. We are giving what is the function, that is x cos x plus 1. Here you can use any function. Then we will be mentioning the lower and the upper limit, that is initial lower and upper limit, a equals to -2 and b equals to 4. Then error value we are taking as any value greater than the tolerance limit, as I told, it is 1. Then k equals to 0, that is to track the number of iterations. C equals to, first we are doing first step, a plus b by 2. Now we are giving this while command, the while loop. Since the error is, till the error is greater than the tolerance value, we are increasing the iteration first. Then we are going f1. F1 is the value of the subs command is used for substituting a value in a function. That is, we are telling subs func, that is in function you substitute, in place of x you substitute a. So this is basically f of a. This is basically f of a. And f2 is basically f of b. Then we are doing again c equals to a plus b by 2. Then we are substituting again, f3 is basically f of c. So now we are saying if f3 is greater than 0, as I told, if f of c is greater than 0, then you have to change the lower limit. That is, your new lower limit a will be equals to c. Otherwise, if it is greater than 0, then b will be equals to c. That is, the upper limit will change. Now here you need to understand the error, because we were telling in bisection method that your root is, the limit of the root is slowly shrinking. So when it converges, basically it converges when your a and b, that is the lower limit and the upper limit, is almost equal. At that point only your convergence or your root is achieved. So that's why we are doing here error equals to absolute of a minus b. So if we do absolute of a minus b, that will basically give me the error. So till this continues, and once it comes out, it prints root obtained is this. So I'll run this. So this is a very simple MATLAB code. Second method also you can do on your own. So if I run this, so 1 second. Those all I'll do. Then I'll run bisection. So it is telling root obtained is 2.073933 in 23 iterations. So now if I want to plot, I think it is not stored here. P is not stored, right? So what we can do is, so we can just store this. So in order to plot this, I'll just store all the intermediate values also in an array in C. A will be equals to C of K. Okay, K is 0, so it should be K equals to 1. So it is telling me that root is same. Now I'll plot it. So you can see here, if I plot this, this is the values of C obtained for all the iterations. Line width, I'll increase it. And 1 second. So you can see the points here. No, this is not the points. 1 second. So here you can see these are the different values of C obtained through the iterations. This is the line width. So these are the different values of C. First it was 1, as I had mentioned. Then it moved to 2.5. Then there was many oscillations, and finally you can see it has settled to around 2.07 using the bisection method. So the number of iterations which was required was around 23. So that is the taker. That is the thing. Okay. Is it clear? Any confusions? Any doubts? Anyone regarding the MATLAB code? Any
No,
doubts?
sir. The
Clear,
code is
right?
clear. Yes, sir.
Okay. Okay. No confusions, right?
Yes, sir.
Okay, fine. So then, okay, time is there. So secant method also, I'll show you the MATLAB code. Here you will do homework. You will do the regular falsy method. Okay. So. mm, So this is the code for the secant method. So in secant method, what was the, it will be, everything will be same. Just there will be two initial guesses, right? So the first is x1, that is the solution is stored in x1 here. So in ninth line, I have written x1 of 1 equals to 1 and x1 of 2 equals to 1.5. These two are given to you. So you'll start from the third value, you will start. And k is 1. Again, error is when it is greater than this much. Then we'll substitute, this is f of x1, this is f of x1, this is f of xk plus 1, and this is f of xk, right? Then basically x of k plus 2, we are using this iterative formula which we have derived previously. So here we are deriving using this iterative formula, x of k plus 2 is x of k plus 1 minus this f of xk plus 1, this formula we are using. Now we are using this error which is f1. F1 means this f of xk, right? So once you have converged your f of x, if xk is your root, then f of xk should be equal to 0. Exactly. So that's why we are using error is equal to f1. So till this f of xk is almost equal to 0, we are continuing this solution. And then k equals to k plus 1, and then we are printing this. So if you see this, just I'll use the clear command. So it is giving me root is around 2.073, same in 7 iterations. So you can see here the number of iterations has reduced. In bisection method, we were getting 23 iterations, whereas in secant method, it is only in 7 iterations. So secant method is a much more, the bisection method is just a crude method of obtaining the root. It is for complex functions. If the bracketing thing is not correct, the initial roots are not properly given to you, then it will take many iterations. Whereas the second method is a much more crisp and much more efficient method to obtain the solution to this equation. Is it clear?
Yes, sir.
The MATLAB code is clear. Any doubts? No doubts? Okay. Okay, fine. Then I'll just discuss the regular falsy method and then we'll stop today's class. So in regular falsy method, it is another iterative technique to solve your nonlinear equations. We have just, it is similar to the secant method only, but it is the iterative formula is just different. The regular falsy method or method of so first I'll explain the geometrical thing, then I'll go to the mathematical derivation. So here also it is the two solutions will be given to you. That is, this is one solution, initial guess, and this is another one, XU. And you take a random XR which is between these two, XL and XU. So then we need to find out what is this XR, right? So now if we draw two triangles here, you can see. So this is one triangle and one more triangle we'll see here. This is one triangle. I'll name the triangles A, B, C, D, E, F. So if we see these two triangles, DEF and ABC, these two triangles are similar triangles. So similarity principle, I'm not discussing that. So this triangle ABC will be similar to triangle DEF. So if it is similar, so what are the sides of the triangle we can see here? So DE is equal to f of XL, right? And your 1 second. I think I've done some mistake here. Sorry. Just a second. X. Okay, BC is correct. This triangle is basically just consider this triangle DE, not C, DEF. No, DEF, sorry. DEC and ABD, ABC. ABC and DEC, not DEF. Sorry. So it is basically these two triangles are similar. ABC and DEC. If these two triangles are similar, we can write the ratio. If two triangles are similar, then we can write the corresponding ratio of the sides are equal, right? So we can write DE by what is the corresponding side there? It is AB is equal to DC by BC. So what is DE? DE is f of XL. AB is f of XU. DC is how much? XR minus XL. And what is BC? BC is XU minus XR. So if you substitute, if you just simplify this, so XR into f of XU, XL f of XU, XU f of XL plus XR f of XL. So if you just simplify this one, you can find out XR. It will be equal to XL f of XU minus XU f of XL upon f of XU minus f of XL. So this is my iterative formula. So what we do is we start with XL and XU. Using XL, XU and the functional values at XL and XU, we find out another point in between XL and XU, which is XR. Then again, we find out f of XR. If f of XR is greater than 0, similar to the bisection method, we change the lower limit. That is, we make XR as the new XL and XU to remain as it is. Again, we do this, repeat the same process, and then again we find out a new XR. Like this, we approach towards the exact solution. Just like it is exactly same as the bisection method, instead of bisecting, that is instead of finding C equals to A plus B by 2, what we do here is we find out, we have a new iterative formula based on the similarity of the triangles, and we try to find out the new value of XR. So you can see here, if you write the code for this, it will be more efficient, that is less number of iterations will be required for it. So I'll just so what are the homeworks? First is the Gauss-Seidel method. So what you have to do in Gauss-Seidel method? You have to report number of iterations required to achieve the solution and the final value of X matrix, and you have to plot the values of X. Also, you have to compare with the Jacobi method. This is the first homework, that is for last week's homework actually. This is week 3 homework. And for today's class, you have to write a code for the regular falsy method. You will take any function as an input. I'm giving you the function also here. So it is basically an polynomial function. So it is x to the power 2.5 minus 12 x to the power 1.5 minus 20x plus 120 equals to 0. XL is given to you 0 and XU is given to you as 10. You have to write the MATLAB code to find the exact solution and report the number of iterations. Report X value and number of iterations. This also MATLAB. Are the questions clear? This homework questions?
Soumya,
Yes, sir.
uh, so in the third last line of this page,
Hmm.
what is the subscript for x on the like x
Oh,
equals to 10? So what
no,
is
no,
that?
this is basically XL. That is the lower
XL.
limit. Yeah, yeah.
Okay,
Hmm.
XL and the other one is
XU.
XU. Okay, upper. Okay, okay.
Yes. Just
Thank
like
you.
I had described here, the
Yes.
notations which I used in regular falsy method, I'm using the same thing here.
Okay.
Okay. So the questions are clear to everyone. So before next Friday, I'll float the Google form and you have to you have to submit the homeworks as well as the feedback for the last class and this class. Any confusions, any doubts? Otherwise, I'll stop the class for today. Okay, fine. We'll meet again in the next class, next Friday, 6:30. Thank you. Thank you, everyone. You can leave.